But we'll get that later. So real quick, before we got a little sidetracked, let's talk about these if-then statements and these domains and kind of different ways or equivalent ways you could write things. So for example, before I wrote that if x is even, we said if, or if the statement was every square of an even number is even. Every square of an even number is even. There's a few different ways you could write that. You could write that as saying for all x, in the integers, x even implies, actually this is a different statement than I wrote before, but it's a statement in itself. X squared, right? Every square of an even number is even. That's saying for all integers, if x is even, then x squared is even. But here's a question. Do we even need a conditional statement to write this? Could you think of a way to write an equivalent statement here without using an implication arrow, without using an if-then? I'll give you a hint. Here we took the domain to be all the integers, and then we said, for this specific part of the domain, we know whenever this is true, this will follow. But what if we change the domain?
Can you define it as like 2z?
Yeah. I'll just say for all x in the even numbers, so the set of even numbers, x squared is even. Right? These two things are saying the same thing. Just here we restrict the domain to begin with. And here we have a more broad domain, but then say for this particular part of it, we have something. That's kind of interesting. There's always multiple ways to write these things with if-then statements. So what if I said for all x in 2, 4, 6, I'm going to say in 2, 4, 30, 1, for any 2, 4, 31, for any number in 2, 4, and 31, if it is less than 10, it is even. So this is a universal statement, right? You could write it as for all x in 2, 4, 31, x less than 10 implies x is even, right? That's kind of a direct translation of what you're saying. What's the other thing you could do?
You could have the domain just be 2 and 4.
Yeah, I just use it simpler. Yeah, I mean, you could just restrict the domain to begin with. For all x in 2, 4, x is even. The point is, if you have any universal conditional statement like this, you could write it as just a straight up universal statement if you change your domain to be just the places where the hypothesis is true. So you make the domain, so if you have for all x in D, P of x implies Q of x, this is equivalent to for all x in, so I want to say what here? For all x and what? Q of x is true. Well, for all x and the things that can plug into P of x and get true, right? All x on the hypothesis, the hypothesis predicate true. But what do we call the set of all things that make a predicate true?
Truth set.
Truth set. Exactly. For all x in the truth set of P with domain D. So you can always do that. You could just restrict your domain to be the truth set of the predicate, right? And then, well, this is saying that whenever P is true, Q is going to be true. So if you restrict it right away to be the truth set of the predicate, you know it makes it true, so Q of x has to be true. It's kind of skipping a step. The point is, you can always do this before you write conditionals. But anyway, I'm over time, so we're done. Any questions?
Another question I had is, does the introduction of variables change the validity of any of the argument forms that we've learned?
Good question. The answer is no, because these variables, right, you still end up, like argument forms, right? So for example, if you had like elimination, right? So elimination says that P and Q, and if you know that not P, therefore you can conclude that Q must be true, right? This is the argument form. But remember, these variables, you know, you make predicates out of them, but you can't put a predicate in here. Oh, I see what you're saying a little bit.
I mean, I think, like, I agree with you. I think it's also still true because you can just evaluate for every point, like every point in the domain, right?
Exactly.
And do it individually.
So this right here, is still totally true, just because for all x and d, right? If for each x, if it makes the premises true, right? I mean, once you plug them in, you get actual statements here. Once you get you're writing here. So yeah, so it kind of doesn't matter because you're always going to convert them to statements before you actually make an argument, kind of. Yeah. Anything else? These are great questions.
Wait, but actually, doesn't that change things? Because sometimes the premises might not be true anymore because of the particular x you plugged in.
Right, but when the premises aren't true, you can no longer make the argument. So the P and Q and not P, therefore Q, this is only saying something about the case where the premises are true. So for example, if you can prove, if we know for all x and d, P of x and Q of x equals true, and not P of x equals true. If you know that going in, meaning you know your premises are satisfied, then for all x and d, Q of x is true by that argument. So you say for all x and d, so for all x and d, I mean, you can kind of do this. So your premises have to be satisfied still. So you have to know you're going to satisfy them.
So like to do this type of argument, you have to be very specific in defining your domain to be equal to the truth set, basically.
Yes, exactly. And what's oftentimes going to happen in math is you might not know everything your domain satisfies the premises, but what you will know is that you can split your domain up, and you can work on cases. You can divide into cases. And so a very nice trick is a lot of times you'll say that, for example, like, what's a good example? I don't know off the top of my head, but the point is, or if you want to say that, like, if you want to say x squared minus x is always even. It's kind of not clear just looking at it why that's true. But when you prove it, you divide into cases when x is even and x is odd, and then it becomes obvious. Because when x is even, x squared is even minus even is even. When x is odd, x squared is odd, x is odd minus odd is even, right? And so you can always say it's even. So the point is, you can split the cases and show that just part of your domain makes the premises true, then use the argument on that part. And then for the other part of your domain, you need to make a different argument to get to the same spot. But yeah. These are all great questions. Yeah. And class is over, by the way. We're just talking now.
Should you stop recording?
Well, these were good math questions, so I wanted to record so people at home and the record
okay.
could kind of get these answers as well. Anybody have any other interesting math questions? Okay, well then I'll stop recording.